So at the beginning of warning that this is actually not my work and not my slides. This was done by Casaccio, Steph, Luc, Baptiste, and Benjamin, and I'm just here to present it. So
Don't ask.
well, we will see. It's a bit like PowerPoint karaoke, I think. So. What is bootstrapping? So bootstrapping is a process that builds a minimal, potentially minimal infrastructure of a language that is a definition of that language. So if you look at an example, if you have a language X, then you want to somehow create all the things in your language via some process, and this can be done, for example, by using another language that has a description and some kind of infrastructure that creates all these objects for you. And there are examples for that. For example, if you look at the wonderfully nice resilient system that was done some years ago by the guy that is now doing the V8 and all the actually and stuff. There you have, as a bootstrapper, you have Java that creates a small talk system to be used in embedded systems. Or you could view even the same language as some kind of bootstrapping infrastructure for a small talk system. And the question that people ask that this work is, the question was they want to understand the bootstrapping, how other people did it, and they did one approach themselves. And the question is, why do we actually need that? And the reason is that we want to have a defined process of creating your language kernel. So if you look at a typical small talk system, then it's actually very ad hoc. I mean, it's just a language that was once created by someone, and if you want to change it, you can reflectively modify that kernel, which is always messy and always difficult and often not fun to do really big changes. So for example, if you would like as a student to take a small talk and build something out of it that has, for example, multiple inheritances or single inheritance or no inheritance at all and something else instead, then it's actually quite hard to change the language kernel while it's running. So what we want is an explicit description that you can change easily, that it has a well-defined initial state, and that kind of controls this problem of reflection that everything is implemented in itself, and if you change one thing, then everything breaks. It's just kind of explicit how it is written. And so if you look at what people did in the past, then there are multiple very interesting projects that have been done. One direction is execution-based kind of creation of small images. So if you look at existing systems that try to kind of build a small talk kernel, then you can see two different big distinctions and approaches. One is that we have something that is dynamic and execution-based. So one nice example of that is Spoon, which takes at runtime, you will later see it in the detail. At runtime, it takes from a second system all the stuff that it needs to run the program. A bit similar was Java, which was done, I think, in South America somewhere. And then there is a second family of approaches that are more statical. So we have a real definition of a program that builds up a small language kernel for your small system. So it's a generational approach to it. And there are two different kind of approaches. One is that you create a small image, a small language kernel inside your smalltalk image, and then you dump it out into a new image file. And that was used with microSuite and with the Hazelnut project that Benjamin did in Build. And another approach is to really have a declarative kind of form, a description that bootstraps the kernel out of nothing. So what we will look at in detail is all these approaches now. So first these three, and then to look at the approach that when implemented for smalltalk to create the kernel there. So Spoon is a client-server approach. The client has a minimal smalltalk system, and every time that the system realizes that for execution it needs something more, then it fetches it from the server. So a similar system to that was Kacharas, which uses more or less a similar approach, but it uses more analysis. So it does not do it for everything that is not there, then it copies it over, but it does a bit more of static analysis so that it copies over bigger chunks of the system so that it's faster bootstrap. microSuite was done, I think, in the context of Scratch or an experiment for Scratch. And this works in a way that that you really have the kernel defined in files, so all the classes and methods that make the kernel, that you load them into a second namespace. So instead of the smalltalk global namespace, in a second environment. And then you need to take care that this is not just loading the stuff from the file, but you need to really take care that all the references are correctly handled. So you need to take care to create stub objects, fix references between classes and meta-classes and superclasses and subclasses and these things. Fix the references inside the compiled methods. And at the end, the idea is to take all this build object graph and save it into an image file. Hazelnut uses the similar approach to microSuite, and it was kind of, so microSuite was done years ago, but nobody knew about it, it was not available. And Hazelnut was started a couple of months, I think, or weeks, I don't remember, before microSuite was then released. And so it uses a kind of similar approach because it is kind of, if you want to have that goal, it's kind of an interesting way to go. Only that it does not have a specific list of methods and classes on disk for a small kernel, but that it actually tries to take the existing kernel of the running smalltalk system to kind of detect what it needs for a list of classes that are needed for the kernel, a list of methods, and then it analyzes all these methods, which kind of other classes they refer to, and then takes all of those and uses them. And the idea here was that it is kind of difficult to have a completely separate bootstrap kernel if you want to at the same time kind of continue to bug fix your existing kernel. You do not want to have two code bases at the same time. And this approach was the idea to have something where if you change something on the current main branch of the system, that the scripts that did this can be kind of easily adapted and used without having completely separate code bases. Bit of discussion about the two approaches. So the big problem of the execution-based approach is that you either need to have always the fallback system available. So you say, okay, I run my small system. It needs something to fetch it from a central server. But if you want to not have that, then it gets really difficult to find out what exactly do I need for my system. Because we do not have a closed world, so we cannot do any kind of static analysis of which methods will be called in the future. So what you need to do is that you need to rely on kind of test suites or things like that to define what you really need in your kernel. And that is always, can always fail in something. And it is actually not really useful for, so one idea of why you want to bootstrap is that you want to change something, you run the bootstrap and have a second system that is slightly different. And this one does not do that. This is just to have a small version, a minimal version of the current defined language kernel. While the static-based approach allows you to really control, I need this class, I need that class, I change a little bit in that class or behavior, and that is different. So this means that this static approach is much better if you want to do changes to the system. But the problem is that you, in practice, you run into this thing that you have your current system that you really use. You have maybe a student that has done the bootstrap and then who maintains the two systems, who merges them when something changes. I think I'm running very, very quickly. As a next step, I want to explain a bit the approach that Gwen took for his bootstrap experiment. So the idea here was to not go the direction of the execution-based ones because of the problems of, that you mentioned, and to actually not use the approach that Microspeak and Hazelnut uses for dumping out an existing small kernel, but to instead really recreate the kernel from scratch with a script. And if you look at what it actually does, is that we first create all the stub objects for literals, so nil, true, false, all characters. Then all the classes and method classes are defined. Methods are compiled in the next step. We need to create some processes. If you want to have a full image, we need process, we need a special object array, all these things. We need some context for the first running process. And then at the end, if you have created all of this, you can serialize it into your image format that you normally use, and then you have an image that you can use in this model system. And the Bootstrap really does all this in the source code like this. Really instantiate all objects, import classes from sources, process the classes, build small objects, save image. And we will see a bit of what this all does. So the instantiate small objects creates first a nil, a true, a false, the character table, and the system dictionary for this new smalltalk system. In the second step, we need to take all the subclasses that we created and really add them to the dictionary. So I think if you look back, we loaded all the code. Let's see if this is my answer. So instead, it's one object, then we imported all the classes from the source code. And then we need to go through all these loaded classes and correctly put them into the environment, into the small dictionary, which is not here. And we need to compile all the methods and install them into this installed classes. So in this system, I think in this system the methods are really taken from a text file on this, so that it really bootstraps from nothing in the end, from a text file. But of course, you could instead take the source code from another running kernel. It would be possible. We need a compiler that can be parameterized by an environment and a special symbol table, because if I recompile now all methods from my new kernel, then it is clear that the environment where it looks for new classes needs to be the new smalltalk dictionary and not the old one, not the current one. And we need to be able to give the compiler a symbol table so that it does not use the symbols of the host environment, but the symbols that it just created in the step before. This means that it needs to have a bit more compiler that is a bit more, I don't know, modular, so that you can actually change these things easily. An interesting thing that you can do at this step is that the methods that you create from the source code are not run. You just build up your object graph and then you dump it out in an image. So that means that at this point you can do all kinds of changes. So you can change, for example, the bytecode. If you have a VM to run, you do images to change bytecode, or do whatever you want. So after we have now compiled all our methods, installed the classes in the method dictionary, we need to start to bring life into this dead thing. Until now it's just methods and classes and nothing else. So that means that we need to fill up the character table, symbol table. We need to really create our processor and install it. And the setup processor really does just that. It creates a process, processor scheduler, and sets off everything correctly so that it has an active process and idle task. Everything that includes smalltalk in this implementation actually needs to have a description of the current running process. Which in this case is this. I don't think that it's too much interesting to see what. You just need to initialize all the minimum amount of objects that you need to run in it. So when it comes up, it needs to have a running process. And as the next step, you so we are now in the stage that we have all classes or methods in our system correctly compiled and done. The system dictionary is correctly filled. We have a processor, we have a process. So that means that we are ready to dump everything out into an image file. And you need to take care a little bit. For example, if you write out the format methods, they need to be special. If your VM needs that, you should not duplicate the things that are requested multiple times. So typical stuff that you need when you write a new image from your system. Only that compared to, if you look at the speak image, how is it called? Image number, I don't know. The tool that writes out a new image format, a new image in a potentially different format. The difference is that this one does not take the whole image, so it does not iterate over all objects, but it just iterates over all objects that are reachable from this run root of your new kernel. And the result of this is a smalltalk kernel that has 54 classes, all the ones that you think that you need. A couple of collections, so all the basic stuff, a couple of collections, some magnitudes, and so, of course, if you look, so for smalltalk, the systems that we looked at were the ones that are described in the literature, at least in some way. I mean, there is no publication about the microspeak at all. It's just a download somewhere. But of course, outside of smalltalk, there are similar systems. So if you look at this, it has something similar. Ruby has a kernel that has some initialization down at C, and then it loads modules, and Python something similar. So the work that was presented is really a very first step. So the main goal up till now was to learn about how to do these things. So it's always a good thing to first analyze what's there before doing something new. And that was the same like if you look at the fuel project. So there was first the image segment, which Mariano analyzed in the first step to see what does it do nicely, what does it not do nicely, how can you improve it, and then out of that the fuel work started. And this is a bit similar. So the idea is to, in the first step, analyze what is there, understand, do some experiments, for example, the hazelnut experiment to do the tracing, kernel creation, or the static, more declarative bootstrap that was like a smalltalk. And to make it real, the next step would be how can we use something like this, one of these things, or maybe a combination of multiple different ways to have a real bootstrap for our system that we use every day. With the idea that if we would have this kind of bootstrap for Farrell, and it would really be the and the result of that would be really the system that we use, then it will be very easy to move the system forward. So if you then have a PhD student or even a master's student, and you want to do an experiment, then it will be very easy to actually do that without learning how to change the running system without crashing it all the time, for example, you normally to do if you do an experiment. That's it. So, any questions? Yeah.
Not so smart question, but first one is I didn't understand well the initializing objects phase. I don't know. The slide was too fast for me. When you the previous says to save the image, you initialize the objects. No. So not just before saving the
gate process. This one.
Yes, that one. I didn't understand what's really happening here.
So what it does is that it creates objects. So the first thing that it does is that it makes objects that represent classes and methods, so source code. And the next step or another step is that you need to create objects for execution. So if you want to really have an image at the end, I mean really an image file on disk that you can give to the virtual machine that startups and does something, then you need more than just code. Because the normal way that the smalltalk system starts is that it is stopped with a programming counter at some place, and when it comes up, it just continues executing that method. So you need to set up all these things correctly. And this is part of it, so that you need a character table, and so this is for blue smalltalk, and I'm not really an expert in blue smalltalk, so I don't really know the real details here. But you need to set up the objects that you need for execution. So in this case, it's the characters, the symbols, and the process, the first process that we want. And part of that is, of course, if you look at the beginning, is this. I mean, these are objects too, and they are actually created at the beginning because you reference them at the end, that they are kind of simple. And you don't need anything that you have not yet.
This work is made with more.
Yes.
Not far.
Yes.
Because the other question was I noticed that in the 54 classes there are also block closure and block context.
I think
and
that the 54.
We can't read of.
I think this one is actually the result of the hazelnut Bootstrap and not of the loose form of Bootstrap.
Hazelnut is that based on far.
Yeah.
Okay, my question applies. Why is still block context there?
So the way that Benjamin did it is that he really just selected a couple of classes that he knew that are central, and then he took everything that these classes referenced and the methods that he selected as required. And as context is actually referenced, not a lot, but in some places in the system, even though it's that code. So it's, for example, referenced in, I don't know, it's referenced in some places that if you just tag methods by wanting this, this, and this, then you get it. It is not a perfect approach. It's just a way of getting something that is smaller and better handled. And it is really an experiment of how to do it.
Just curiosity, how big image that is resulting?
I don't know actually. I don't know. Once when I asked, I think it was at 2 megabyte, which is not too small for a small image. But that I don't know what this 54 classes are.